Okay, we're going to look at the net force, and we're going to use Newton's second law here. We're going to use the force equals mass times acceleration. And we're going to talk about what happens when we've got more than one force. So the resultant force is also called the net force. And we usually either say F with the subscript net, or we talk about the sum of the forces. Okay, that little funny symbol means sum. It means we're going to add them all up. So usually more than one force is acting on an object, like in the tug of war below. In order to work out the effect of these forces on the object, we need to calculate what's known as the resultant force. So remember that all forces have a direction unless, of course, they're zero. So if forces act in the same direction, we're going to add them. If they're in the opposite direction, we subtract. And remember, it does not matter who is positive and who is negative. What matters is that you're consistent. So if there's anything going this way, it's plus, and this way it's minus. Or, if you want, this way is plus, and this way is minus. It doesn't matter, because you're just going to interpret your answer in terms of the sign, and you're going to interpret it in terms of the direction. So whatever you choose, it's going to work. You just got to be consistent. Okay, so let's solve the above diagram for the resultant force, also known as the net force. So we're going to say, all right, well, let's call this one force 1, and we're going to call this one force 2. So when I talk about the sum of my forces, and I'm talking about them in terms of the vector, I want to add these vectors together. And when I'm adding those vectors together, I'm going to put in their magnitudes, but then I have to account for their direction. So if I'm going to make this way positive and this way negative, then that means I have a plus 450 and a minus 490. Add them up and you end up with a minus 40 newtons. And what does that mean? This is the part where you come in and you interpret. And you say, therefore, the net force is 40 newtons. Minus means, oh, this direction. So that would mean 40 newtons left. Good. All right. Let's solve for the net force for the car below. Again, we've got two forces. We've got the car pushing 10 newtons. We got this parachute slowing it down 7 newtons. So again, we've got opposite directions. In this case, I don't know, up here I did right was positive. Let's make, I don't know, let's make this way positive and this way negative. Whatever. Same thing. So let's see. The sum of my forces is going to be equal to the mass times my acceleration. So the sum of my forces, let's figure that part out first. So the sum of my forces is also known as my net force. And to get that, I need to take the force 1 and force 2, and we're going to add them vectorially, which means I'm using pluses and minuses to show the directions. So I'm going to have a negative 10 and a positive 7, just because that's just the way we chose our symbols. And we end up with negative 3 newtons. So therefore, the net force is 3 newtons. And in this case, negative means to the right. I didn't close my bracket. Oops. Okay. So now when we want to find acceleration, we now have a net force, so we can now use F equals ma. Okay, good. Let's do it. So I know the sum of my forces is equal to the mass times the acceleration. So my force net is going to be equal to mass times acceleration. So my net force is 3 newtons, and we're going to keep that O to the right, so that's negative, equals the mass, which is 6 kilograms, and the acceleration, oh, we're looking for that. Well, let's just rearrange here. Instead of multiply, we're going to divide both sides by 6. Therefore, my acceleration is negative 3 divided by 6, which is negative 0.5. Acceleration is meters per second squared, and it is negative left, which means therefore acceleration, oops, I'm in a space, is 0.5 meters per second squared to the right. Notice how my net force and my acceleration are both in the same direction. This is very important. F net and acceleration in same direction. Okay, that's pretty key. Yep. Very important. Same direction. Same direction. Okay, let's do some more. I have some pretty complicated examples here today. So unfortunately, Google Docs didn't have an arrow that I could use. So let's not forget that these are all vectors with the exception of mass, which is a scalar. Right? So mass is just a number, it's a scalar. And forces and acceleration, those are both vectors. So we got to worry about their size and direction. All right, let's see. Two people are dragging a canoe out of a lake onto a beach using light ropes. Each person applies a force of 60.0 newtons forwards on the rope, and there's a force of friction that's exerted by the beach on the canoe, which is 85 newtons backwards, which makes sense, eh? It's probably a pretty heavy thing to drag up, and the sand is probably pulling it backwards. So the first thing we want to do is a free body diagram. And let's remember that a free body diagram always starts with a dot for the object. In this case, it's the canoe. The canoe is my object. We need two people, each with a force of 60 degrees north. So I'm just going to call it A for person one and B for person two. I don't know, you can use ones and twos, doesn't matter. And then we have our force of friction. So remember, force of friction with the little f is going to be going backwards. So there's my force of friction. Now it is on the ground, so I do have a normal force because it's on a surface. And we are on the planet Earth, so we do have a force of gravity coming down. So check free body diagram. Done. B. Calculate the net force on the canoe. Well, nothing, there's no information for up and down. We're going to assume that this thing is only going sideways. So we're going to assume that the sum of my forces in the y direction is 0. Okay. So we're going to assume that there's no vertical motion. But we don't know about what's going on in the x direction. So in the x direction, I have my force from one person. I have my force from my other person. And I have a force of friction. So we say we add the vectors and then we bring in direction. So let's call this way positive and this way negative. So we're going to have a plus 60 because there's two people. And then the force of friction is now going backwards, which means we're going to have a minus 85. So in the forwards direction, we have 120 newtons. In the backwards direction, we have 85 newtons. So what does that give us? 35 newtons forward. All right, that's not too bad. Yeah, so that's our net force. Our net force, which is, in this case, the sum of the forces in the x direction. All right. Now, if I want to know the mass of the canoe, or sorry, if I have the mass of the canoe, can I figure out the acceleration? I sure can. So the mass is 36 kilograms. The acceleration, well, that's what we're looking for. And I know my net force is 35 newtons forward. So in this case, we can use good old F equals ma. So my net force is gonna impact my mass and my acceleration. So let's see, we got 35 newtons going forwards. We have a mass of 36. We want to find our acceleration. Let's divide both sides by 36. And 35 divided by 36 gives us an acceleration of 0.97 meters per second squared forward. Now, if the canoe is not bouncing up and down, so here's where that sum of the forces in the y direction is 0. What is the force of the normal? All right. Well, there's no up and down, which means the sum of my forces in the y direction is 0. So that means that the sum of the forces in my y direction, well, I've got to take my normal and I'm going to add that to my gravity, right? They're vectors. We're going to add the vectors. And I'm going to say that up is positive and down is negative. We have to add up to 0, so my force of my normal is going to be positive. Oops. And I'm going to subtract off the force of gravity. The force of gravity is commonly calculated as mg, so mass, and the acceleration due to gravity. Which on planet Earth, we use 9.8 meters per second squared. So that means bring that over to the other side. So mg is going to be equal to my normal force. We have a mass of 36. An acceleration due to gravity of 9.8. So that gives us our normal force, which is going to be equal to 3.67 newtons. Therefore, the force of the normal is 3.67 newtons, and the normal is pointed up, away from the horizontal surface of the ground. Good, good. Doing pretty good here, folks. All right. Now let's stick 2 athletes on a team, Ben and Owen. They're going to practice to compete in a canoe race. Ben has a mass of 70 kilograms. Owen has a mass of 75 kilograms. And the canoe has a mass of 20 kilograms. Ben can exert a force of 400 newtons forwards. Owen has an average force of 420 newtons forwards. And during paddling, the magnitude of the water resistance on the canoe is 380 newtons. So let's see, let's do a free body diagram here. So there's my canoe. So here's my free body diagram of the canoe. And what do we know? Well, the canoe is on the water and we're on the planet Earth. So we're on the planet Earth, so we got a force of gravity. We're on the water, so we have a normal force because that's what's, keeping us up. And then we said we had a forwards force. And that's the force coming from Ben. And then we have another forwards force, and that's the one coming from Owen. Force of Owen. But then we also had the water resistance. And resistance means it is in opposite direction because it does not want you to go. So that's my resistant force. So usually resistance is our friction force. So you can call it friction. You can call it R for resistance. I don't care. Same thing. So we drew our free body diagram, and now we need to figure out our initial acceleration of the canoe. Well, you can't figure out acceleration without the normal or without the total forces. So let's see. Sum of our forces in the x direction equals mass times my acceleration in the x direction. We're not going up and down, so we can ignore the y. Let's see. In the x direction, we have the force from Ben, and we have the force from Owen, and we've got the force from the water resisting us. Let's keep with the R, sure. And that's going to equal the mass times the acceleration in our x direction. Ben is a plus 400. Okay, let's keep forwards as plus, backwards as minus. Keeps my brain happy. Owen is going to have a force forwards of 420. That resistant force is the 380, and that's opposite, so 380 equals, oh goodness, I still need the total mass. Total is going to be the mass from Ben, the mass from Owen, and the mass from the canoe. So we need to add those all up. So we've got 70 plus 75 plus 20, so that 165 kilograms. Let's stick that back up in our equation. So our mass is 165, and no, we don't know our acceleration. We're looking for it. So in the forwards direction, we have a total of 820 newtons. In the backwards direction, 380. Mass of 165 times our acceleration. Let's clean that all up. So what do we get? 440 equals 165 times the acceleration. Opposite of times is divide. So let's divide by 165, divided by 165. Let's see, acceleration is 2.67 meters per second squared forwards. Nice. All right. Word problem. Therefore, the initial acceleration of the canoe, because that's what we're talking about this whole time, initial acceleration of the canoe is 2.67 meters per second squared forwards. Nice. Good stuff, folks. Oops, sorry. Should we do another one? Are you ready to try some on your own? Why don't you try this one on your own? See how you do. Good luck, guys.